Hi, and welcome to this presentation about careers in the nuclear industry. My name is Mike Slee, and I'm a team leader and principal gamma spectrometrist at Jacobs. Today, I'm going to go through the role that I have, how it relates to the nuclear industry, and how I ended up getting into the nuclear industry. My role is team leader and principal gamma spectrometrist. But what does one of these actually do? Well, I work within one of the largest commercial radiochemical laboratories in the United Kingdom. This is where we carry out radiochemical analysis for a wide range of customers, from EDF, where we support their power operations to ensure that the lights stay on in the United Kingdom, all the way through to research experiments such as CERN, where we recently supported the decommissioning of one of their science experiments. Now, I manage the high resolution gamma spectrometry laboratory. And where does that fit in? Well, gamma spectrometry is a non-destructive technique that is able to identify a significant number of radionuclides in one measurement. And it uses the physics behind gamma radiation to identify and quantify gamma radiation in a customer's sample. But why is that important, I hear you ask? Well, it can help decide the waste route a sample should take to ensure that its impact on the environment is minimised so that it is stored and decays away safely and correctly. Secondly, gamma spectrometry also supports our customers in ensuring that they do not exceed any regulatory limits to public health. What is gamma radiation? Well, gamma radiation originates when an alpha or a beta decay produces a daughter nucleus in an excited state. We can think of this as holding an object at a height. When we hold the object at a height, it has stored gravitational potential energy. And when we let go, it falls to the ground. As it falls to the ground, it transfers the gravitational potential energy it has into kinetic energy. It's very similar in the radiation world, where the daughter nucleus in the excited state wants to get to ground state, and it does so by emitting a gamma ray, otherwise known as a photon of electromagnetic radiation. Now, the gamma rays have no charge and are unaffected by electric and magnetic fields, and we can't see them around us, so how do we detect them? Well, gamma radiation could be identified by something as simple as an absorption experiment. If we take the case of alpha radiation, now the alpha particle has a large mass, but because of this, it is less able to penetrate through matter and is stopped by something as thin as paper. As we move to beta radiation, the beta particle is of a smaller size and therefore is able to travel further through matter and therefore is stopped by something like wood or plastic. As we get to gamma radiation, now as I said earlier, this is not a particle but is a high energy electromagnetic radiation, a bit like an X-ray. It has no mass and can only be stopped by something as dense as lead. So doing that experiment, we're able to identify the different types of radiation. But how do we quantify it? Well, in the gamma spec laboratory, we use detectors that are able to discern the energy imparted by each gamma ray on the detector. And we do this by using suitable detectors that have been selected using the physics behind gamma ray interaction with matter to ensure that we use a detector that is suitable, has a suitable interaction material, and that the probability of interaction of a gamma ray with the detector is maximised. So the images below show examples of gamma ray detectors. On the left is an example of the type of detector that we use. It's a high purity germanium detector. So on the front is like a silver cylinder, and this is actually where the detector material sits. And as you move along it to the back, you can see a large beige cylinder, and this contains liquid nitrogen, as this is required to keep the detector cool so it's able to operate. On the right, we actually see the reality of our setup that we would need in the laboratory. It is significantly bulkier, and it stands at about 5 foot tall, and the beige grey object you can actually see is actually a shield, and we need this thick lead shield because, as we learned on a previous slide, the gamma ray radiation can only be stopped by something as dense as lead, and we really require something like that so that the measurements that we take, we don't get the background, but we're able to get the low levels of gamma radioactivity just in the sample. As well as managing the high resolution gamma spectrometry laboratory, I'm also involved in an exciting new project, development of the Rolls-Royce small modular reactor. Now, this reactor is a consortium of many nuclear companies based in the UK who are working together to create a reliable and stable solution for electricity production, able to help achieve net zero carbon emission challenges set by the UK government. Due to the limited time I have today, I haven't been able to really go through all of that. So what I've done is I've attached a link of Roger Harrison of the BBC giving an overview of SMRs. At school, my teachers imparted an enthusiasm during my physics lessons. So much so that I knew I wanted to pursue a career in nuclear physics. So I ensured I studied the STEM subjects: science, technology, engineering, mathematics at school, and all the way through to A-level, where I studied physics, mathematics and geography. This enabled me to get to university, where I studied for a bachelor's in physics with medical applications. This taught me the physics behind the interaction of radiation with matter, and how we can not only use this to treat, but also detect medical conditions. I then went on to do a master's in a course called Radiometrics, Instrumentation and Modelling, again at the University of Liverpool. This focused all I'd learned on my BSc course so that I could optimise systems for the detection of radiation. This opened up an opportunity to do a PhD, and I did this work on a technique called Compton imaging. This is where you are not only able to identify and quantify a radionuclide, like in the high resolution gamma spectrometry laboratory, but also locate its source of emissions. The knowledge and the skills I'd learnt from school all the way through university has put me in an excellent position to get the role I currently have in the nuclear industry today. My top tips for a career in the nuclear industry are: first of all, ensure that you're doing a STEM subject. You really want to be making sure that you're doing your physics, your chemistry, your mathematics. You know that these courses will help you get into the industry. Make sure that you get involved in clubs and societies. When I was going through university, I was part of the Physics Society, and I was a committee member. Not only did I get to know more people, I also ensured that I was kept up to date with the latest advances in physics. I've then carried this on through to my career, where I'm now a committee member of the Nuclear Institute Northwest branch. So I'm able now to keep in touch with the latest advances in the nuclear industry and also get to know a wide range of people across the industry. I'd also say it's hard work, but it is worth it in the end, you know, to reach your goals. You know, I love working in the industry, and I'd recommend it to anybody. I'd like to thank you for taking the time to listen to this presentation.